So you'll see, especially with function composition. Okay, so cotangent inverse x, what is it? An angle. What will I do next? Yes, so x equals cotangent alpha, which means there is a right triangle somewhere with an acute angle alpha. And we do know something about
hypotenuse of 1.
Cotangent. Cotangent is the reverse of tangent. Tangent would have been opposite over the adjacent. That's okay.
X over 1.
Yes, x over 1. X over 1, which means this is the square root of course, x squared plus 1, because it has to be the sum.
Why is it?
Say it again.
Why is it 1 plus x?
Because it's x over 1. It's a ratio.
Isn't the hypotenuse 1?
Cotangent is the adjacent over the opposite leg. Because tangent is the opposite over the adjacent leg. Cotangent is the adjacent leg over the opposite leg. Only sine and cosine involve the hypotenuse. Nothing else involves the hypotenuse. Although secant, I should say, is, you're right, or even secant, because secant is 1 over cosine. So secant will involve the hypotenuse indirectly through cosine. And cosecant will involve it through sine. But tangent and cotangent do not involve the hypotenuse. Okay? So tangent alpha is this over this. Cotangent alpha is this over this. And the longest side, which is the hypotenuse, has to be the sum of the squares of the legs with the square root on top. Okay, it turns out that we don't even need it. So what is this? This is tangent alpha. 1 over x. Is this okay?
Oh, yeah.
Now we can change the problem and say tangent of sine inverse. So where do I start now? Yes, so then sine inverse x equals alpha.
X equals
Yes, x equals sine alpha. So this is a new problem. And then, yes, so there is an angle alpha. And now, yes, now this is x over 1. Because it's the opposite over the hypotenuse. Correct?
Yeah.
So now how do I determine this leg? Well, this time I have to subtract. From this squared, I subtract this squared. Because it's a leg. I add these two squares when I look at the hypotenuse. I need to determine the hypotenuse. But if I need to determine a leg, it's a square root of the hypotenuse squared minus the other leg squared. Is this okay? And now what am I asked to determine is tangent alpha. So what does tangent alpha equal to?
That's a root, so square root of 1 minus x squared.
Very good. Very useful for Calc 2. If you need Calc 2. Okay, anything else? Is there any other problem? Anything else that you would like to go back to? Anything else?
I think I had a question.
Yes?
Would it be a question about the shaded
You mean the area?
area?
Oh, yes. 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 We had a problem like that.
Yeah.
In which we were given some circle and an angle, central angle, and we were asked to determine the area of the circular sector. Yes. Yes.
But then we have to revise the formula, right?
Yes, please. Yes. Anything else? Anything else? Okay. If you don't have anything else, I'm not rushing you. Then I will start chapter 7, only because we are doing trig anyway. And then I'll come back to chapter 4 for test 3. Anything else for me?
So today we're going to cover 7.1, 2, and 3. Or
We'll see. We start chapter 7. That's all I can say. But this is not going to be on this test next week. Or starting from Saturday, if you want to take it Saturday. Anything else for me, Paul? Well, you still have Monday next week and Wednesday next week to ask questions. But I do recommend redoing the problems we did in class first. Okay? And if you come up with something anytime, we'll look at it. Okay, chapter 7. Chapter 7 deals with very interesting things. It's so-called the Analytic Trick. What are we going to look at in this chapter? A lot of identities. Of course, we are going to start with the usual ones, the basic ones, and we're going to build on them. And we are going to identify more identities. And the most important section in this chapter is solving trig equations, which basically it's covered at the end of the chapter in 2 different sections. I have to be honest and say that students, when they get to calculus, very few of them remember how to solve trig equations. So it's really sad for me, because I think that that trig equations are really important. They're up there with quadratic, with rational, with absolute value, with you name it, right? Substitution. If you remember, we substituted when an equation was quadratic in form. And what we learned in chapter 4, we're going to learn two other types of equations here. So equations are really important. So when we get to the last 2 sections, when we discuss, actually there are 7.5 and 7.6. These are the 2 sections of trig equations, but we only cover the first one. But I'll show you a few examples from the other one as well. I will not test you on it, but I'll show you something from 7.6. So equations are, in my opinion, are very important. Yes, go ahead.
I'm just asking a question. So why are we going to chapter 7 before chapter 4?
Only because we've covered trigonometry already. So I want to finish trig. 7 is the last chapter for trig.
Okay, or something else.
These are not connected in any shape or form. This deals with logarithmic and exponential functions, and this deals with trig. Since we already finished 5 and 6 in trig, and this is the last chapter of trig, we'll do this first and then this.
Okay, yeah, it makes sense.
Only because we already have all the trig identities so far fresh in our minds.
Right, yeah.
Because if I do this, then I will have to come back and say, hey, do you remember? Yeah,
No.
right.
No.
So I want to avoid you doing that to me. Okay.
Okay.
So, few things that we are going to look at here. Trig identities. Half angle identities. I'm just giving you an idea of what to expect. Double angle identities. Sum difference. Identities. Sum to product and product to sum. Those formulas will be given to you on the test, however. That's why I don't need to mention it right now. And trig equations. So these are the general topics here. I don't have anything to say in section 7.1 because we already covered what 7.1 is all about. And the title is Trig Identities. How many trig identities we know? Or forget about their number, just give me what we know already. Identities. An identity has a left-hand side, an equal symbol, and a right-hand side. That's an identity. If I just say 5 is not an identity. But if I say sine squared plus cosine squared equals 1, that is an identity. So, what is the first one we talked about? Good. What was the second one we talked about? We cannot forget the other two that come from here.
Sine squared is equal to 1 minus cosine.
That's good. Yes, sine squared x equals 1 minus cosine squared x. That's good too, but I was referring to the other two. And yes. So you can also say cosine squared equals 1 minus sine squared. That's true too. But I want the other two that come from this one. And you can say these two come from that one too. I would agree. Yes, they do. When we do what to this identity? What do we do to this identity to get the other two? Yeah, but I get in trouble if I multiply because I don't know yet what sine squared cosine squared is.
Tangent squared. 1 is equal to s equals 1.
Awesome. How did we get this one? What did we do here to get this one? By
cosine squared.
Awesome. Exactly. We divided this by cosine squared to get this one. Perfect.
And the other one is just by sine, right?
Good.
So
Sine squared.
Yeah, 1 plus.
If you want to keep them in the same order, it's fine too. Oops. Cotangent squared plus 1, but you can write 1 plus cotangent squared is the same thing. What does it equal to? Yes, cosecant squared. Very good. We know more than just this. Here's another one. Sine pi over 2 minus alpha. What did we say this equals to? And that is an identity. Okay, let's say we don't remember. Here it is. This is alpha. What is this angle? Okay, right. Pi over 2 minus alpha. Very good. Good. So let's say I'm going to say this is A, B, and C. So can anyone give us sine of pi over 2 minus alpha? Perfect. What else in this triangle equals A over C? Because they have to be the same. Left and right have to be the same. What else? Yes? That's it. So these are the co-function identities. We looked at them some time ago. So these are called function Identities. Identities. Give me another one or two more. I want to write down two more of co-function identities.
Cosine. 5 plus 2 minus alpha. It's the same as sine of alpha.
Good. Now I want tangent. Make one up with tangent.
Are we still using pi over 2? Okay.
Same thing.
Okay, yeah.
Same thing.
Tangent of pi over 2 minus alpha. Same
Yes.
as
Look at this. If you have any doubts,
Secant.
co-function. The co-function of tangent cannot be secant or cosecant. It must be.
Oh, cotangent. Sorry, cotangent alpha.
Let's check. Tangent pi over 2 minus alpha is a over b.
Yeah.
What else is a over b?
Adjacent tangent full drops.
Cotangent of alpha.
Yeah.
A over b. So these are the co-function identities. Okay?
Seems to be a path.
Yes, absolutely. Absolutely. Okay, give me one more. Let's say cosecant pi over 2 minus alpha. What will that equal to?
Secant.
Exactly. No, not pi over 2.
Secant that.
Exactly. Secant alpha. Cosecant pi over 2 minus alpha equals secant alpha. So sine is the co-function of cosine. Cosine is the co-function of sine because of this property or these identities. Tangent is the co-function of cotangent. Cotangent is the co-function of tangent, and so on and so forth. Okay. So in this section, first item is simplifying trig expressions. I'm not saying identity, I'm saying an expression. Simplifying trig expressions. On page 498, please choose from 13 through 26. 13 through 26 on page 498. If you don't choose, I will.
18.
Which one?
18.
Very good. 18 it is. So secant x minus cosine x over tangent x. Simplify the trig expression. Very useful for calculus and beyond. Okay. What is the idea here? The idea is to go to the simplest possible two trig functions that we know of, and they are sine and cosine. All the other four functions depend on sine and cosine in some way or another, either on both or one or the other. So I'm going to go as simple as possible, and of course I will not change cosine into anything because I can't, but I will change secant into 1 over cosine, and then cosine stays, and I will change tangent into, very good. The denominator stays as is for now, but I have to do something with the top. I don't have square root. I need to find the, very good, the least common denominator, which is only 1, which is cosine x. And then what do I have at the top? Remember, this is over 1. Cosine was multiplied by 1. All the other rules apply. Okay, so what is the top? I do have an identity. Which one?
yeah.
Sine squared x.
Equals 1 minus cosine.
Very good. So I will continue with sine squared x over cosine x times cosine x over sine x. So the top fraction is indeed sine squared over cosine x. I copy it first and then flip the denominator because I'm dividing two fractions, multiply by cosine over sine. Now remember, I always say you have to state restrictions, you have to state restrictions, you have to state restrictions. Here, I should have written from the very beginning that cosine x is not 0. And of course sine x is not 0, right? Because if one or the other is 0, the whole thing collapses. I don't even have an expression. So assuming that all conditions are fulfilled and the expressions exist, are not undefined, then now I'm ready to simplify. And how do I simplify? What do I do? Well, of course, cosine with cosine go away. Not the x, not the cosine, but cosine x with cosine x. And one sine x with one sine x. And the simplified form is sine x. And I know that I can't go simpler than that. This is it. I cannot give a recipe that works in all situations. It depends on the problem. However, always keep in mind what I said from the very beginning. Factor simplify, factor simplify. Keep things as simple as possible, if that problem allows. Okay, we choose another, or we move on.
Maybe 15.
Okay. We haven't looked at these handouts for a long time. They're not forgotten. I want to work on this for a moment. What will you say about this? It's an expression. Simplify. So we have the square root, and we'll come back to other problems in a minute, whatever you want. So we have the square of 9 sine squared x plus 9 cosine squared x. So here's what I'm tempted to do. I'm tempted to break a radical and say the square of this plus the square of this. But you can't.
Yeah.
You should shoot me if I do that, of course. You're right. So what can I do? And the answer is the other key word that I've been repeating forever. They go together most of the time. Okay, so what will I factor?
9.
Yes, I have to factor 9. What is left in parentheses?
Sine squared x plus 7.
And what does that mean?
1.
Yes. So this is the square root of 9, which is?
3. Oh. Yay.
So now, look at the rest, and please choose. Many of these are from the book. They are selected from the book. Please choose. And honestly, after you take this test, what I would do if I were you, I will do all these problems and check the answer in the back, because the answers are here. Okay? So please choose anything you'd like to work on, and then we'll pick another problem from the book if you want, and then move on. What am I doing?
No, so I have to find my handout. I can't.
It's the big one. Okay?
About
9? This one? Okay, very good. So in number 9, we have cosine theta over secant theta plus sine theta over cosecant theta. And we said what? We said that we want to stay as simple as possible. Sine and cosine are very simple, but secant and cosecant are not. So I will keep in mind, assuming all conditions are fulfilled, because if secant is 0, although secant cannot be 0, because secant is 1 over cosine. A fraction is 0 only if the top is 0. So 1 over cosine cannot be 0. And the same thing with cosecant. But keep in mind that we have to always worry about the conditions being fulfilled. Okay. And I replace this by 1 over cosine, and then plus sine theta, and I replace cosecant theta by 1 over sine theta. And then I have to flip the denominator, because that's how we divide fractions. The top is cosine over 1, and the bottom has to be flipped. So what do I get?
Cosine squared theta plus sine squared theta, which is 1.
Not too bad, but we have to have the foundation of the identities. Without those, I will look at it and say, good, anything else? We cannot do this just yet. It's coming up. We're not there yet. We cannot do this just yet, and we cannot do this just, we could do this one, 23, we can. But this one we cannot do just yet. We don't have all the information. For example, I was surprised that you picked 9, because 12 is way more difficult. I shouldn't say way. 17, 18, 19.
Let's do 1.
Okay, please choose anything you want.
Start at 12.
Okay, let's start with 12. I wanted you to pick 12. If you didn't, I would have. Let me tell you why. Because we have an agreement. That's why. And this is extremely important. Again, as we observed here with trig, the first and the basic is sine squared plus cosine squared equals 1, pretty much. The same thing in algebra. If I don't know what a plus b times a minus b is, or a plus b squared, or a minus b squared, I don't have too many skills in algebra. So that's what I'm saying. That's why I started with that. So when I look at this, I know what I have to do. What do I have to do? And we have an agreement on this. Exactly. I have to be able, because if I have that in the back of my mind and I review it and I repeated it, then I'll see it quickly. Otherwise, I'll get stuck and look at it and I will not know where to start. Yes, it's the difference of squares. And now how do I write it? Once you say the difference of squares, you'll come up with 2 binomials, sort of binomials. They're not binomials. X plus 2 is a binomial. Cosine is not a binomial.
Cosine squared x plus sine squared x, and then cosine squared x minus sine.
That's it. That's it. And now, the first one is 1, and the second one we cannot completely finish it just yet, because we have to get to section 7.3 to completely finish it. But it is wise to change at least that at this point in time, to change one into the other. And not have 2 trig functions in an expression, if possible.
Oh, that's substitute.
Yes, which one? Normally we'd like to keep sine. But you can say, I prefer cosine. I'm fine. I cannot force you. There is no not specific rule here. So if you want to keep sine, then you will replace cosine squared by 1 minus sine squared x. Minus sine squared x is 1 minus 2 sine squared x. And I'm going to say wait until 7.3. And we will finish it then. This equals something from 7.3, but I can't jump over 7.1 and 2. I'm sorry? No, it's cosine twice alpha. It's the double angle. No. It's the double angle. It's this. But we haven't gotten there yet. So we can write it right now, and then we'll come back later. So this is cosine twice x, like this. It's It's not cosine twice and then x. The argument is twice x. But again, we don't have the knowledge of this just yet. Okay, now the second part, and we'll come back. We will come back to more problems from here. Okay? So just don't forget, don't let me.
Like we can do the first 11 or so, right?
Well, yes. We'll have to exhaust all possibilities from there. So we will come back to it. Okay. Now the second part here is prove trig identities. That's the second part of section 7.1. So why do I need to prove trig identities? If there are identities, the left-hand side equals the right-hand side. Why would I have to work on that? And is there a trick question? No. If I'm told, prove this identity, I have to show that the identity is true, but there is no trick question, meaning it happens that the left-hand side does not equal the right-hand side. No. If I'm told this is an identity that's carved in stone, but I have to do one of the three possibilities. One possibility is I start with the left-hand side and I work my way to the right-hand side without touching the right-hand side, just peeking from time to time. The second possibility is I start with the right-hand side and I work my way to the left-hand side without touching the left-hand side at all. I just say, here, this side simplifies to this. The third possibility is I have to simplify both sides to the max, and then I'll say, see, they are the same. If they are the same, and they have to be the same. So anything you'd like to pick from 29 through 90. Same page, 498, 499. Anything you want. Number 29 it is. Really? Never mind.
Well,
I'll pick.
I said
No way. You're going to do the 29. I'm going to do 44. And please choose wisely. 1 minus sine x over 1 plus sine x. They claim equals, we can do 29 of course, secant x minus tangent x, everything squared. So one more time, this is not a tricky question. This is an identity. I just have to show that I can start from the left and show that it equals the right, or I can start on the right and show that it equals the left, or I simplify both sides to the same quantity. Now I have to make a decision. Where do I start? And the answer is left or right. Look carefully. You want to start with the most complicated one, because it's, of course, because it's difficult from nothing to get this, but it's easier to get from here to almost nothing. So in this case, I start with the right-hand side, and I write that. Right-hand side equals secant x minus tangent x squared. And I start working on it without doing anything to the left-hand side. Okay, what would you recommend we do to the right-hand side? And if you say squared, I will say no, because I want to simplify inside if I can to the simplest possible, and then square.
So you change secant to 1 over cosine, and then tangent to sine cosine.
I also have to be honest again and say this. Sometimes I am able to see the path before I start. How to get from here and what's going to happen to get that. But sometimes I'm not able to. When I'm not able to see the path, I still have to do something. I have to start with the most difficult part or complicated situation and do something to it. I may see in my foresee the steps, but if I don't, I will still have to start somewhere and do something. Okay? Good. So what do I do next? And always remember, factor simplify is always valid.
Yeah, the same denominator, right?
Very good.
1 minus sine x cosine.
So I have 1 minus sine x over everything over cosine x. So I said, okay, the top has to be squared and the bottom has to be squared. Again, this is from algebra.
Oh, yes, you said.
Good. Which one should I work on? Now I peek. And this is not cheating. I peek. Where am I going? Oh, I want one of those to stay.
Yeah.
So I'm not going to destroy this. So where do I look then?
The bottom.
Right. And what do I know about the bottom?
Then it equals something.
Yeah, thank you. That does it.
Well, it's an identity.
No, it's
1 minus sine.
much further.
And we have an agreement on the bottom.
Difference of squares.
Correct. So what do I do?
1 plus sine x, 1 minus sine x.
Assuming all conditions are fulfilled, always keep that in mind. What will I do next?
Now you
Factor out 1 minus sine x on the top and
can
bottom.
cancel.
And what is this?
So that's left side.
This is the way we prove identities. Some of them are hairy. Not all of them will be done in 2 or 3 steps. Some of them require more. Good, so now please choose. If you want 29, we can do 29.
I just solved it.
I know. So please choose from 29 to 90. Anything you want.
So 29.
Except 29. Okay, anything from 30 to 90.
75.